Hello and welcome to the next lecture on IT security, and the topic of today's lecture are firewalls. Let me start by giving you a brief outline of today's topics. We're going to look first in a quick introduction what firewalls actually are and why the idea of firewalls came up. Then we're going to address the components of a firewall. We're also going to look into firewall architectures. We are going to address some of the conceptual weaknesses in firewalls. And last but not least, we're going to finish the lecture by taking a closer look at personal firewalls. So let us start with the introduction. The internet, as you already know, is rather a network of networks of different institutions like universities, companies, and others. And it's not a single network, it's a network of networks. The network within one single institution is typically referred to as the intranet, and the intranet usually is connected to the internet, and over the internet, arbitrary machines connected to the internet can communicate to other arbitrary machines connected to the internet. So basically, without any other means of protection, any machine connected to the internet could connect to all of the machines in the intranet. And conceptually, it doesn't make a difference whether this is a machine contacting, let's say, the server from the room next door, or whether it is a machine contacting the server that is sitting or that's residing in some internet cafe at the other end of the world. So from the security perspective, however, there are good reasons to think that the machine in the room next door is somewhat more trustworthy than the machine from the other side of the world. However, that's the situation. Anybody can connect it to the internet, could without further mechanisms connect to any other machine in the internet, and institutions running intranets often think, for good reason, that the machines within their own intranet are somewhat more trustworthy than the arbitrary machines coming out of the internet. Why is it that intranet operators think that machines on their network are more trustworthy? Well, typically all machines within the intranet are administered according to the same rules and regulations. The IT policies for all of those machines typically are identical. Moreover, the machines are operated, if they are operated in the intranet, typically through members of the same institution, namely the institution running the intranet. So you know that the machines are all in, let's say, equal shape, and a shape that has been, well, that's considered sensible. And also, of course, you know who the users are. So in that sense, access to the intranet, as in contrast to the internet, is somewhat regulated with respect to which machines can be operated in there and what users are allowed in there. So in the intranet, there might be special services which are solely meant for members of the institution running the intranet, and which should not be reachable from other networks through the internet. So for instance, there might be some server which has some information which is only meant for the employees of the company, which should not be accessible from the outside. And also, in general, it is not a good idea to allow arbitrary machines from the internet without any further measures access to resources in the intranet, for instance, because it is possible that these machines are basically running attack on the other machines. So in summary, it's not a good idea to allow all machines in the internet to arbitrarily use services which are provided in the intranet, and that of course then requires to do something against it. Many institutions really require intranets, and there are services in the intranet which must be used. So we need the intranet, but we somehow need to separate the intranet from the internet, and that's what we do by use of a firewall. What is a firewall? Well, a firewall is placed on the position connecting the intranet to the internet and controls the traffic between both networks according to rules. According to these rules, also called policies, the firewall distinguishes between allowed and unwanted traffic and can also, well, filter out and stop the unwanted traffic, as is depicted here in this picture you see. Depending on size and type of intranet, the firewall in fact can consist of a lot of different types of components. We will discuss packet filters and application level gateways today. We will also discuss different architectures for firewalls today, but again, most importantly, firewall sits on the boundary between the internet and the intranet and, well, controls the traffic between the two networks according to certain rules, or you could also call them policies. I also use the term rule because we're later on also going to use the term rule for one type of component of firewall, namely the packet filters. So if we have a firewall, then of course the intranet does not turn into an area where security is no longer an issue. In principle, none of the security threats which are present will be totally eliminated by using a firewall. Particularly problems that still remain unresolved if you operate a firewall are, first of all, that there might be insiders in the company that are also trying to, well, do espionage or do other illegitimate activities. So those cannot be stopped by a firewall. Moreover, if there are legitimate stations in the intranet that have been compromised, for instance laptops, which you carry over the boundary between intranet and internet every day, then also you might have malware already running in the intranet, and then the firewall cannot stop any of this as well. Moreover, there might be certain loopholes and security vulnerabilities still that allow access directly to the intranet, circumventing the firewall for attackers from the outside. That could, for instance, be the case because there is a different connection between the internet and the intranet that you haven't thought of. This might be, for instance, somebody connecting his or her machine through UMTS to a wireless network, and if that machine acts as router, that might be an entry point for an attacker into your company's network, and you might have some, let's say, publicly accessible Ethernet ports where people could connect to your intranet immediately, or there might be other security vulnerabilities due to design implementation or insufficient policies in the firewall itself. That also is a very big concern. So again, not a single security risk gets completely eliminated by a firewall. Nevertheless, as you recall, it's good to have a layered architecture when it comes to security, and a firewall can be one layer of security that you put in place. It's also fair to say that typically within an institution, not all members of the institution have access to the same type of data. And that also, of course, means that additional access control mechanisms on web servers, databases, and other services which run internally are still necessary. They are also necessary because, again, the firewall cannot be trusted completely with respect to eliminating any security risk. So all of the security measures that you would have to take without a firewall still should and need to be taken if you are operating a firewall. A firewall is a useful and important part of the protection of a network, but it's not a single solution. So let's move on to the components of firewalls. We are going to address two types of components, namely packet filters and application level gateways. Let's start with packet filters. All firewalls today consist of multiple components, except for the ones you might have at home in your DSL router. Those basically only have a single component, namely the packet filter, which we're now going to talk about. In general, the packet filter is an indispensable component for all firewalls, and as we've already seen in the previous chapters, header information in packets and of course also the information coming from higher layers, particularly the transport layer, already provide a plethora of information that could be used for filtering the data and for distinguishing between wanted and unwanted types of traffic. Typically, packet filters are built into one of the intermediate stations, aka routers, on the networking layer. However, again, they are not restricted to taking into account only network layer information. Most, well, virtually all firewalls also take into account information from the transport layer, and also some of the headers in the application layer are often considered as well. There are other technologies that go deep into the payload of all of the packets. That's called deep packet inspection, and with techniques like this, even other types of protocols, or I should say occurrences within application level protocols, can be found by these types of packet filters. However, here we're going to stick to the basic type, which only takes into account header information up to, let's say, header information on the application layer. So typically packet filters are built into routers or other intermediate stations. Since all of the traffic between the intranet and the internet traverses a router between the two, if there is a packet filter on all of the machines connecting the two networks, then indeed all of the traffic can be controlled by the packet filters and be analyzed. There are other means of operating packet filters as well. Packet filters can also be operated as transparent devices. If you build a packet filter into a bridge, which resides on the data link layer, then you can still filter out based on the same information. However, such a firewall is going to be transparent to the machines or to the packets traversing them, because there will be no indication within the packets that they have actually traversed a device. Whereas if packets traverse a router, as you know, then at least the time to live field is decreased and other things will be done as well. How are packet filters structured? Well, packet filters consist of so-called rule chains. What is a rule chain? A rule chain consists of one or more rules and a so-called default action. So here you see a typical rule chain consisting of a number of rules as long as a default action. So a packet that is compared against the rule chain will basically go to a rule. What is a rule? Well, a rule specifies features a packet can or cannot have, and it also has an action part, and if the packet matches the features which are specified in the rule, then the specified action of the rule is executed. We're going to look into this in practice for Linux. So again, a rule consists of features a packet may or may not have, and if the specified features in the rule apply to the packet, then the action for that rule is executed. If the specified features do not match, then the packet is compared against the features of the next rule. If they match, again, the action for this rule is executed. If not, packet is compared against the next rule. If there is no match, compared against the next rule, and so on and so forth, up until either there is a match. And again, the first match, or the rule where we have the first match, that action is going to be executed. If there is no match whatsoever for all the rules in the chain, there is a specified default action which will then be executed. What could a potential action or default action be? Well, again, it could, for instance, say, please discard the packet, do not let it traverse further. It could be the decision that the packet is to be forwarded, for instance, in a router, or further processed within the own machine. And it could also be the jump into another rule chain. So you might have a rule here which would say, all TCP traffic, please go to my special chain which I built for TCP. Most packet filters allow the users / administrators to create their own rule chains for particular tasks. So that's how a packet filter works in principle. And again, when a packet comes in, there is a certain rule chain where the examination of the packet will begin. And then again, the rules are went through in a sequential fashion. And wherever we have the first match, that action is what's to be applied to the packet. Since it might be a jump into another rule chain, it can well be that the packet will undergo further examination in that rule chain as well. So that's the basic functionality for packet filters. And the typical configuration for packet filter allows for two types of default action. One type of default action is to explicitly or to allow everything which is not explicitly prohibited, which basically means that the rule chains here, if you specify it that way, specify what you don't want in your network. So it would basically say, if this is something I don't want, discard it. This is something I don't want, discard it, and so on and so forth. And if a packet traverses without a match, then the default action would be to accept the packet. That's why this is called default accept, where everything is allowed which is not specifically specified up here. And then there is the other choice you have, namely default deny, which basically means here you say, please discard what ends up here, and up here in the rules you specifically specify what's supposed to be allowed into your network. And again, that's called default deny. So we have default accept and default deny as typical configurations or paradigms, if you will, for packet filters. And of course, reality isn't black and white. There are also packet filters which are configured in a mixed configuration where both of these techniques are combined. Since in general the order of the rules, particularly if you are using a mixture, is very important, you really have to be very careful with respect to such mixed configurations. In principle, it really doesn't matter which type of configuration you use. You can achieve the same level of security with both, but of course you have to be very, very careful with respect to the actual rules and how you specify them, and again in what order, to not unintentionally let packets pass which are actually not meant to be in your network. So again, the order of the rules is important. Let me briefly explain this to you with an example. So Here is an example of how in a mixed packet filter configuration the order of rules actually matters. Let me just jump out of this here and go into a notepad. Okay, so let's assume we have a mixed packet filter configuration and we have two rules. Okay, first rule says drop all packets to to IP destination address X, and we have another rule which says accept all packets where protocol is TCP and TCP destination port equals 80. Again, we're going to see more detailed examples on how a packet filter operates and how actual rules look like in Linux a bit later. This is just meant as an abstract examples where we have two rules. And now let's assume we obtain a packet here which comes in, which happens to have, among others, the IP destination address is X, protocol is TCP, yeah, and the TCP destination port happens to be 80. So again, there are lots of other features here in the packet as well, which we don't want to consider further. But let's assume we inspect this packet with a packet filter, and the order of rules in the packet filter is A, then going on to rule B. So again, rule A means that all packets are supposed to be dropped to IP destination address X. Could, for instance, be that this is an IP address of a server where we don't want to allow any connections to because the server has, for instance, malware on it. Or it is more typical that we would not allow traffic to certain IP address ranges from a particular network. Rule B typically would mean that we are going to allow traffic which is outgoing request for HTTP web pages on a server. That's typically what TCP port 80 means. Of course, any other TCP connections to port 80 would also be allowed. That's one of the problems with firewalls. Let's not go into those details too much now, but let's just take a look at what happens with this packet. So what happens if we start in a packet filter where we first have A and then B? Then basically, of course, we take the packet and we first check the features for A, and A basically says IP destination address is X. If it's X, then we're going to drop the packet. So what happens here, since the IP destination address is X, this rule has a match and the packet will be dropped. So what happens if the order of the rules is reversed? B and then A? Well, you can guess. Rule B says that all packets are allowed through when the protocol is TCP and the TCP destination port is 80. Now, here the protocol is TCP and the destination port is 80, so this rule matches, which means that the action is executed and the packet is accepted. So, depending on the order of rules, the way this packet is treated is different. So that means that particularly in mixed configurations, you have to be very, very careful with respect to how you order the rules. So one question you should also ask yourself is, is it possible that something like this also happens if we only have rules in the rule chain where the action to be executed is accept and the default action is deny? Is it then also possible to construct an example like this? And what happens if we reverse it and say that all of the rules have a deny and the default action is accept? Is it then possible to come up with an example like this? And the answer is, and please think about it and write down why at home, that it is not possible to construct an example like this. Basically because, of course, in order to get a different treatment of packets here, the order of rule only matches if the specified actions in the rule can differ. So that was our example, and let's move on now to another important distinction in packet filters, namely static versus dynamic packet filtering. The differentiation between static and dynamic packet filtering is important because what we've considered up to now are only features of the packet which you can basically extract from the packet itself. Yeah, you can just check things which are specified within the packet. So we are looking into header information from the data link layer. It could be from, which is however a bit untypical, from the networking layer, meaning particularly IP addresses and type of transport protocol, transport layer information, and well, sometimes we could specify application layer information as well. However, this doesn't make too much sense often, because if you really want to use application layer information, you're much better off with an application level gateway, which we're going to consider later. However, you can try to distinguish between different types of applications based on the source and destination port of the transport layer protocol information. So for TCP and UDP, there are special conventions which would, for instance, specify that HTTP servers would always wait for incoming connections on port 80, which basically then mean if you see something that's destined to port 80, that's supposed to be HTTP, web browsing, and then you could say, okay, I will generally allow TCP, which is port 80, which means I allow web browsing, but I don't want to allow people to, write email and then send them out from my intranet, which would mean that I block port 25 for TCP, which is the standard port for SMTP. However, that's only a convention, and you can run arbitrary services on TCP port 80 if that transport protocol is TCP. And in fact, that has really happened. If you take, for instance, a look at what update functionality in, well, the most common operating systems on PCs these days do, they would always, if they are looking for updates, use TCP port 80 outgoing. And the reason for this is that, of course, the programmers know that sometimes the machines reside behind firewalls, and it's very likely that TCP port 80, if something is open at all, would be an open port, whereas many other ports might be closed. So that's only a convention, and it really doesn't help that much. However, again, might be a first line of defense. Well, again, we might filter on transport layer protocol information, such as, for instance, then also the destination and or source port numbers. We could also differentiate packets based on which interface on a machine they came in. So there are interfaces which go into the intranet, interfaces which go into the internet. That might be very important information. We could filter based on IP source or destination address, most commonly specified in the form of IP address ranges. And we could specify, of course, the transport protocol and source and destination port on the transport layer as already outlined. Other important factors might be flags, particularly in TCP. And well, sometimes you would also filter based on date and time. So, however, what we've not considered right now is that the decision in a packet filter might not only solely be derived from the packet itself, but also factor in additional information that this packet filter already obtained, particularly about previous packets from the same communication flow or communication connections. So this differentiation is the difference between static and dynamic packet filtering. In static packet filters, the packet is only considered itself, and only information contained within the packet will be considered when filtering out the packet, whereas in dynamic packet filters, also information gained from previous packets might be taken into account. So whereas in a static filter in general, I just see the packet and I have no idea whether it's the first, the second, or the nth, or whatever packet of a communication flow. In a dynamic packet filter, and that's the most important application of it, you will basically be able to distinguish between the first packet of a communication flow, and for the first packet you make a decision as to whether to allow this type of communication or not, and then for all subsequent packets belonging to this communication flow, you will basically enforce the same decision which you already made earlier. So again, for static packet filters, the decision of the filter what to do with the packet is solely depending on the packet itself, whereas for dynamic packet filters, previous occurrences of packets might be factored in. That's also why static packet filters are called stateless, whereas dynamic packet filters are called stateful packet filters. We'll also see stateful and stateless packet filters in action under Linux later on. So how could we use a static packet filter to distinguish between incoming and outgoing TCP traffic? So in a static packet filter, again, we take the packets at face value, and the ID to distinguish between incoming and outgoing connections is of course an important one, because typically in a configuration for an intranet you would allow people from the intranet to not restrict them with respect to access to services in the internet, whereas you would not like to allow incoming connection requests from the internet into your network. And let's now consider how to distinguish between incoming and outgoing TCP traffic in a static packet filter. So this is the situation and how we want to achieve it. Namely, with TCP, we have a connection set up by means of the three-way handshake. And what we are going to do with the static packet filter is basically we are going to disrupt the three-way handshake if the connection is established from a client in the internet to a machine in the intranet, whereas we're going to let the handshake go through fine if the connection is going from the intranet to a server in the internet. Basic idea how this can be achieved is shown here. So what we can basically do is, if we look at the three-way handshake, then for a connection from the intranet into the internet, we see that there is a SYN going from the intranet to the internet. To be very specific, what you can actually see is you see an IP packet which carries a TCP segment with a set SYN flag. Then in the reverse direction, we are going to see an IP packet with a TCP segment where the SYN and the ACK flag are set, and then the intranet machine is going to respond with an IP packet where we see a TCP segment with a set ACK flag. So that's the typical three-way handshake: SYN, SYN, ACK, ACK. And again, if we allow SYN through from the intranet to the internet, then we allow the SYN ACK through from the internet to the intranet, and then again the ACK in this direction, then we can allow the setup fine. So the only thing we really need to do is we need to block, when we want to disrupt the three-way handshake here, we need to block either the SYN from the internet into the intranet. That's the best option we can do, because then basically the intranet machine does not see anything with respect to the connection setup. It is also instructional to allow the SYN in this direction through and then filter out the SYN ACK here. That would not be a practical firewall filter configuration, because then you bother these machines with connection requests which are not going to succeed anyhow. However, you should try that out if you have a chance to try that out in the lab later as well. Because then basically you would not allow connections in this direction or established from this direction. So basically servers in the intranet could not be contacted from the outside, whereas servers in the internet could be contacted from the intranet. So far so good. Now of course when you say allow, do not allow, again we want to block this. There is a problem however with a static configuration, because as you know, once a TCP connection is being set up from the perspective of TCP and the transport protocol, we have a full duplex connection in both directions, which means there is no distinction whatsoever between who initiated the connection, or who was the client, and who accepted the connection, meaning who was the server. And I'm talking about the transport layer, of course. So in that sense then, both communication peers are equal after the communication has been established, which means that from this point on, where the communication is established, we're going to see TCP segments with set ACK flags flying in this direction, and so on and so forth. And we'll of course see two-way communication between the machines, and all of that needs to pass through the firewall just fine in order to allow connectivity established from the intranet into the internet via TCP. And that opens up a problem, because if somebody from the internet would fake a TCP segment where an ACK flag, for instance, let's say, is set, and which seems to go into the intranet belonging to a TCP connection which has been established fine, then a static packet filter would basically need to let this pass through, because it might belong to a legitimate connection. And again, the filter is stateless and has no idea what ongoing connections and communication flows are currently established. And that might then trigger a response from an intranet machine, or bother the intranet machine, which might allow somebody in the internet to then gain certain or gather knowledge and information about what's happening in my network. So that is a problem somehow, because again, with a static packet filter, I cannot do anything against this type of spoofed traffic. So I can basically then try to see what type of reactions I would actually get. So what about dynamic packet filters? Well, again, as I mentioned before, with a dynamic packet filter, the decision of the filter, what's to be done with a packet, will not only depend on the packet itself, it might also depend on packets which have been previously seen. That's why this is called stateful as well. So what are the advantages of a dynamic filter? Well, the advantages of a dynamic filter are apparent. The just mentioned vulnerability for static packet filters, that some attacker from the outside might spoof a packet and then put this packet on the wire and go through the firewall just fine, is basically eliminated, because a dynamic packet filter would know that this is the first packet, or that is a packet not belonging to any ongoing communication flow, and would then basically be able to discard the packet. For a dynamic packet filter, dynamic packet filters can also see whether UDP packets which come in belong to a communication flow which has been seen before or not. So also it's possible for UDP to distinguish in which direction the first packet of a communication flow is going. So in that sense, also for UDP, it would be possible to distinguish between quote unquote incoming and outgoing UDP traffic, particularly with respect to initiating the communication flow. And that of course is also a big advantage of dynamic filters, whereas for static packet filters, again, if I see an incoming packet, it might or might not belong to a communication flow which is already established. So you already get the point that dynamic and stateful packet filtering are more advanced with respect to security features. So why would we then have static packet filters at all? Well, reason is that, of course, implementing a static filter is very simple because all packets are taken at face value. No further information about previous packets or connections or communication flows need to be stored. And that also means that load balancing is very simple because you can throw any packet where you like if you have multiple instances of static packet filters and want to make a decision. Whereas in a dynamic filter, of course, you need information about the previous packets or, let's say, connection or communication flows, which also, of course, means that the hardware requirements are higher than for static packet filters. And with respect to redundancy and load balancing, static packet filters are very easy to implement, whereas dynamic packet filters are, of course, harder to implement because all of the instances when it comes to load balancing would need to have access to a commonly kept database of already ongoing communication flows or connections, unless, of course, you're using other mechanisms to ensure that all packets belonging to a particular communication flow would always go to the same packet filter. Well, so much for filtering and static and dynamic packet filters. Let's move on to problems and limits of packet filters. So, packet filters are a useful tool to control the traffic between two networks, to filter them, protocol it, and also, in some cases at least, to change and manipulate packets. However, packet filters do have a couple of limitations which can also lead to vulnerabilities or to the situation that packet filters cannot remedy situations that you actually would like to remedy. So among the disadvantages of packet filters, there are a couple which are particularly noteworthy, and we're going to note those down. So problems and limits with packet filters. So the first we have to mention is there is no user-specific or application-specific filtering possible. So, in other words, packet filters can take static or dynamic information according to the packets they get in order to make a decision as to whether to forward that packet, drop that packet, or do whatever. But that also means that what the packet filters see in terms of where the packet stems from, they don't see the user or the application that has created the packet. What they solely see is the IP address of the packet, so where the packet was generated and where the packet is going to. And in case there are numerous users using a single machine, all of the packets, no matter which user they're from, will have the same IP address. By the same token, all applications running on the same machine, no matter what type of application, will also have the same IP source address. And what that also implies is that with a packet filter at least, it would not be possible to say that SMTP traffic, meaning email, could only be generated by, let's say, an email user agent and not by other programs, which perhaps could be malware or whatever. This is clearly not possible because, again, this information is not to be found in any of the packets. So that's a first very severe limitation, but of course there are others which are equally severe. If you want to differentiate between different application protocols, the only way of typically doing that is to use the transport layer information about source port or destination port respectively in order to identify these applications. So let's note this down. Use of transport layer information to identify application protocols. So this is something which we've already briefly discussed. There is, by convention, a certain ports on transport protocols are reserved for certain types of application protocols. So for instance, server side listening on port 80 should imply that the traffic which is going to that port is HTTP, Hypertext Transfer Protocol. However, this is of course not guaranteed because it's just a convention. So some servers, for instance, would deliberately use other ports, and then by the same token, other applications might use incoming port 80 in order to circumvent certain filtering mechanisms by packet filters. And that also means that if certain ports are blocked because certain applications are not wanted, then this can be circumvented by simply using port numbers which are allowed. We are going to look at this in some more detail later when we discuss tunneling. Another thing I'd like to mention is that, of course, fragmentation can be problematic. While fragmentation, again, is becoming increasingly important, the fragmentation of packets can also lead to the situation that particular protocol information, for instance on the transport layer, which is required for filtering, is not present in the packet because the packet is fragmented and only the first fragment would carry this information. So that's also something that might be problematic. There is another thing which might be problematic. There are certain applications for which the port numbers which are used might change. So an example for this would, for instance, be the FTP, File Transfer Protocol, but there are others where basically port numbers are or could be negotiated dynamically through a control channel, and then the actual data channel is different. So that poses a problem for packet filters. Let's note this down: applications with varying port numbers. And then there is another limitation, which is basically tunneling and encryption. So what does this mean? Well, again, some protocols allow for tunneling other protocols by basically encapsulating information from one protocol into another protocol. And if you do this, of course, then in a packet filter that might take header information at face value, wrong conclusions might be drawn. But that's not the end of it. It gets far worse when encryption is also implied, because if encryption happens, then of course packet filters are not in the position to break the encryption and extract any information from the encrypted packets. So once packets are encrypted, packet filters basically have no clue of finding out what's actually in the packets, and that also means that all of the filtering mechanisms in packet filters basically cannot be applied to encrypted traffic. And that, of course, is a severe problem, particularly as more and more traffic is encrypted over the network. And we'll also discuss problems with tunneling and how to best deal with it in future chapters. So, so much for the limitations of packet filters. The limitations of packet filters are one of the reasons why application level gateways are employed. And we are going to look into application level gateways after discussing another topic that better fits into the packet filtering domain, which is network address translation. So we already mentioned in our recap on networking that there are certain IP address ranges which are solely intended for use in private networks, as these addresses are not routable through the internet. And it is very common that such private IP addresses are used within intranets. But since they are not assigned to any network particularly, it's again impossible to route those through the public network. So if a machine with a private IP wants to use services in the internet, then this must be realized by some form of converting the private address into a public address. One way of how this could be done is to use an application level gateway, which basically has a private and a public IP address. We are going to take a closer look at this once we discuss application level gateways in more detail. But it's also possible to do a translation with a packet filter and basically allow machines with a private IP address to access the public internet through UDP and TCP, namely by using network address translation. Network address translation is specified in certain RFCs, and it's particularly common in smaller nets, in home networks. Basically, one of the reasons for this is that as the range of IP addresses is limited, most people, if they have a small network at home, would only have a single public IP address. So they would basically use different private IP addresses within their network and then translate those to the public IP address for contacting services in the internet. We will discuss NATs, and we'll also discuss the security ramifications of employing NATs. So we will not distinguish here between other types of netting. There also in literature you'll find network address port translation. We'll subsume all of this here under the term NAT. So this picture here you see on the slide basically shows the basic way a NAT works. So what you see here is you see an intranet here of the private address range within the intranet is used, and here you see two machines A and B who have the private IP addresses. So A and B are private IP addresses, and when A and B want to contact the internet, they route their traffic through a machine which has the private IP address C on the interface into the intranet and a public IP address N for its interface into the internet. So that basically could, for instance, be a home router which is employed. So to be able to contact the public network at all, then we must of course have this public IP address. And netting works with a single as well as multiple IP addresses, but in the following we'll only consider a single address, which again is assigned to the public interface of this machine here. So since private IP addresses cannot be routed in public networks, the idea is basically when a packet comes in here from A or B, what happens is that the IP address A or B is replaced by the public address N of the net. So by doing this, packet goes into the internet, and if you, for instance, would then contact machine D or E, what they would see is the address N, and when they reply here, then this packet with address N would add up here, and N then basically somehow needs to find out the translation done and then see whether this traffic is meant to be sent to A and B, and how to then replace the public address. Now, of course, there are a sort of restrictions on what has to happen on nets. So, as you know, each TCP connection within the internet is uniquely identified by the tuple consisting of IP source address, IP destination address, TCP source port, and TCP destination port. If you make such a translation, you must make sure that this unique identification remains intact, and that could, for instance, imply that it's not enough to simply translate IP addresses, because if in this scenario here A and B would, well, by chance contact a TCP, both contact the machine D here on port 80, both using source port, let's say 45678, then of course by translating the addresses A and B here both into N, you would not be able to uniquely identify each of the connections, and that basically means that in such a case there must also be a translation of the port numbers. In this case, of course, then the TCP source port numbers from the view of the clients. So that also needs to be taken into account, and this becomes particularly problematic when also UDP is considered, because whereas for TCP you always have a handshake and a connection setup, this is not the case for UDP, and that is responsible for all sorts of problems which might happen. By TCP connections, the situation is very simple, because the net machine can basically observe the first packet of the three-way handshake, and then it can basically make, basically set up a translation consisting of a IP address translation and a port translation of the TCP source port if necessary, and then remember this, and in case something else then comes up that would conflict with this, it can make a different translation. So that's particularly simple, but things get a bit more messy when we also consider UDP. Now, what happens is that this translation is of course stored in the NAT, and the type of translation which is done is called a so-called NAT binding. And here you see an example of such a binding. Something comes in from A port X destined to destination D port Y. Then here the NAT translates this into N port Z destination DY. Of course, the destination cannot be changed. And if then something comes in from DY to NZ, this is going to be translated into DY AX. So the NAT binding here is AX gets translated into NZ. Particularly with respect to UDP, there are different types of NAT who will basically do different things. So there is a so-called symmetrical NAT where for the translation, IP source address, IP destination address, transport protocol, source port of the transport protocol, and destination of the transport protocol are taken into account. So that basically is, well, taking all information into account that you could have, and this information of course then also is stored as the binding in the machine N. If you want to simplify that somewhat, then you can come up with a so-called cone net, where the IP address and ports of the external communication peers are irrelevant, and only the internal addresses and ports are important. This has all sorts of implications, because basically it would also allow, depending on the type of NAT, whether it's a cone NAT or a so-called restricted cone NAT, other machines where the binding was not set up for, to use the same incoming port number and still get packets through. So for a so-called cone net, there are 3 variants. Again, we don't consider the external partners, we only consider the translation that was done here internally for such a cone net. And there are 3 types of cone nets. There is full cone net, where an existing binding is used for all incoming and outgoing packets, which basically means if there is a binding, as you see here, that would bind, for instance here, AX to NZ, then it is basically okay. Any of the machines D or E can basically use the port NZ here and send something, and it's always going to be forwarded to AX. And it is completely irrelevant as to what port this stems from, server side wise, or which machine it stems from. All of these packets here will happily go to NZ, whether it's from DY, DW, or EY, which basically means it may be from the machine that was actually contacted here and the same port. It may be from another port on this machine, or it may be from an arbitrary port on this machine here. Then there are 2 further net types, namely restricted cone nets. In restricted cone nets, the basic restriction here is that the packets which are translated must come from the same communication peer. So in this case here from machine D. From other machines it's not going to be used. There's also port restricted cone, where basically the packets that are translated must also be from the same port that was contacted here. Well, these are the net variants. The net variants are important because these types of bindings can make all sorts of problem. If you have, for instance, a port restricted cone net and you're not accepting packets that come from a different source port but the same machine, or from a different machine, that may impede the connection setup, for instance for voice over IP, where ports are negotiated and the machines negotiating the ports are perhaps not the same that would actually be the ones contacting the machine where the connection is to be set up. So, okay, let's briefly talk about security aspects in net. First of all, when I'm using a net, there is a certain anonymization going on, because no matter whether it's A or B, what the communication peers see here will only be the net address, and that can be good, for instance, in a small to medium business that only has a single external IP address. I would not be able to find out which of the employees did what when I look here into the logs on the servers, because all of them would come in with the same IP address. So there is a certain form of anonymization. If I'm using symmetric nets, then of course, if they are configured in the right way, then they basically block incoming connections unless there is something set up that sometimes on the routers you can buy for home use is called port forwarding. It's no port forwarding, it's actually basically a hole that you open up, because of course for incoming connections there is no net binding set up. So if something contacts N here on, let's say, port 80, there needs to be a specific rule already specifying where to forward the traffic, namely to here or to here. And if I don't set up any of these rules, the net is basically not going to allow anything in. So basically it blocks effectively all incoming traffic unless I'm poking a hole into the net myself. So that is a very useful security side effect of a net. However, that only holds, of course, for symmetric nets. For the cone nets, it is possible also that somebody's contacting me from the outside, particularly if the net is not restricted. So if a net is properly configured, that can also help to foster the security of the machines behind the net. But since it's not a security mechanism in the first place, it is important to also use a firewall in addition to using a net. So let's take a look at a practical example of packet filtering under Linux. In order to study packet filtering under Linux, I've set up a reference test network as is depicted here. Our reference test network basically consists of two institution networks. One institution network is shown here. The other institution network is shown here, and both institution networks are connected to this network here, which basically serves as our model for the internet. So let us take a specific look at the individual machines. So let's start with the client machine here in this company's network. The IP address range of this network is 192.168.10-24, so it is a regular network, and this machine here has address 192.168.100. So here is the machine, and as you see, there is not much happening on this machine yet. Then going back to this network, we of course also have a router. The router has two interfaces, one of course into the 192.168.10-24 network, and the other one into the public internet, which is the 172.16.20-24 network. So it's also a 24 network here that we've chosen. Of course, we could as well just as easily have used other network addresses as well. Here we are using private addresses for all of the networks, while of course in general at least this year would have been a public IP address range, and for now we also assume that all of these addresses here can happily be routed. So we use private addresses, but we treat them as if those were public addresses. Let's switch to the router here, which again has two interfaces. Here's the router, as you can see. Then in this public network we do have a client machine, and the client machine you see here. And let's move on to the company network, where we have a router, can be seen here, and in this network we also have a machine, which is this machine. So regarding IP addresses, you see the setup here, and what I'm going to do is I've configured this machine such that it's able to observe all the traffic that flows through the public network, our model of the internet. And what I'm going to do now is I'm going to start a packet sniffer, particularly Wireshark, on this machine. So Wireshark's now running, and what I'm now also going to do is I'm going to ping from this machine here to 10.24.37. As you see here, we get requests and responses. Let me stop the ping for now, and let's check what we, again, the ping went from here, of course, through both routers and the public network to here. And again, this interface here is promiscuous, listens to all the traffic in this network, so we should have observed the ICMP messages going back and forth. And as you can see here, that's exactly what we get. We do have the ICMP messages here, so we have the echo request from 192.168.100 to 10.24.37, and we have the answer from 10.24.37, the echo reply, which is the answer to this ping. What you see before here is the ARP request of 172.16.24 for the address of 172.16.25. So basically that's of course the router in the network 192 asking for the MAC address of the router in the 10 network. So going back to this picture, ARP request from here for the MAC of this machine. Obviously that's necessary because there was no traffic before, and you can see all of this works out fine, and then you see lots of echo requests and replies going back and forth, and you see another ARP request up here. So let's go stop the capture here and start the capture again. So I start the capture again, but what I want to do now is I also want to show you something. We've already talked about manipulating routing, and of course I'm not going to manipulate routing here, but what I want to show you is basically also how routing can be changed through particular messages. So this here again is the machine in the public network, and if I check .routing configuration here, what you see is basically that we've configured a default router here, which is 172.16.2.4, where all the traffic will go from this machine. So let's take a look at this picture. 2.4 is the default router. This is this machine here, of course. So if I'm now sending traffic from here and I'm trying to ping this machine, then of course the traffic is going to go from here to here, and then this router is going to forward it to this router, and then the traffic is going to be sent to this machine. Of course that is not very efficient, because basically the traffic is relayed within this network twice, and that's why what's going to happen is we expect an ICMP redirect to be sent from this router, telling this machine that it's much better to send traffic directly to this router here for 10.2.4.37. And of course this is an example of a legitimate ICMP redirect, but this could also have been created maliciously in order to redirect the traffic to this router if, for instance, this was under the control of an attacker. So I just briefly want to show you this as well. So the packet capture is started, and what I'm now going to do is I'm going to ping 10.2.4.37 from here. Everything has worked, and you already see in the terminal here that it says I'm pinging the machine, and from 172.16.2.4 there is an ICMP redirect to 172.16.2.5 sent. So basically then the packet is going to be rerouted. Let's take a look at this in Wireshark. So here is what we see. Forget about the ARPs for now. Of course the MAC addresses must also be asked for before something could be sent. So here you then see the ICMP echo request from 172.16.2.4 to 10.2.4.37. But of course this is not sent to this machine, it's actually sent to the default gateway. Let's just briefly check that it's being sent to the default gateway by checking the Ethernet addresses. What you see here that this is destined to VMware 633103, and as you will see here, this is exactly the address of 172.16.2.4. So as we would expect, traffic is being sent there, and we then get the ICMP redirect from here, and then we see a retransmission of the packet. This time the packet is not being sent to the machine here with the address 3103. This time it's being sent to C9D9, and C9D9 of course then, or C9DC, I'm sorry, is of course 172.16.2.5, as you can for instance see here. Okay, so that's the ICMP redirect, and then you see the reply, and there's the next request, and as you see there is another redirect, but then I think packets are being sent directly. We could check here. So what you see here is that it's being sent to C9DC, and C9DC, as mentioned before, is machine 0.5. So that's what you see here. 0.4 is in fact the machine with the address 3103. Okay, so again, if you are not familiar with the details of routing and why it is possible to now identify where the packet is actually being sent by the MAC address, please brush up on your knowledge on networking. Of course, networking is a required prerequisite for following this IT security lecture, as mentioned numerous times. Okay, so that was that, and as you see, the ICMP redirect here is a powerful tool, and there is no authentication happening here, so somebody used that maliciously in order to get hold of traffic that was in the network. That at this point would have been possible, and we would have had no means of preventing this right now according to the scenario that we are currently studying. So let's move on to the actual packet filtering, and before we do this, I'd like to explain a bit about how packet filtering works under Linux, and for this we are going to take a look at how the network filtering under Linux is architectured. Packet filtering is done under Linux with the so-called netfilter, and this is the Linux netfilter architecture. So how does this work? Well, basically, if there are three different chains, there is the input chain, the output chain, and there is the forward chain. And the packets start in chains depending on whether they are from a local process outbound, whether they are destined to a local process, or whether they are actually to be routed through the machine. If the packet is not to be routed, then of course it's for the machine itself, and it's going to go through the input chain before, if the packet is accepted, it goes to a local process. If a packet is generated by a local process, it goes through the output chain if it's for an outbound interface. And if a packet is coming in, is not for a local process but actually destined to be routed out on another interface, it's gonna go into the forward chain. So all that matters for us right now is of course the forward chain, because we are going to place the filtering functionality on the routers, either this router or that router. That pretty much is up to what we want to do. For now, we are going to use this router here in order to try out what's happening. So again, here is the router, and what I will do now is I'll basically take a brief look at how the filtering currently is configured, and the command for doing that is called iptables. And if I want to list what's going on in detail, then the command is verbose and -L. For lists, we can take a look at what's happening in terms of rules. So as we see here, there's the input chain, the forward chain, and the output chain. There are no rules in any of these chains, and all of them have the default accept policy, which basically means that every traffic through this machine here is gonna pass fine, and also traffic to and from this machine will not be filtered. The firewall at this point doesn't do anything. So what we're going to do now is we're going to again go for an ICMP ping, and again I'm going to start capturing in the public network. So this again is the machine 172.16.220, which we are going to use for capturing all of the packets. And what we will do now is we will simply, again, as we did before, ping from 10 to 4, ping 10 to 437 from 192.168.100. So let's start doing this, and if I take a look at the capture, then you again see the requests and replies going back and forth. Now let's go to the router. Here's the router, and what I'm now doing is we will insert a rule into the rule chain, forward chain, which will basically tell the firewall to drop ICMP packets. And the command for doing that is I want to add a rule to the forward chain, and the protocol which I want to filter out is ICMP. So every ICMP packet is going to match this rule, and the action for this rule is going to be drop. So let's put this rule in. There it is. And the question is, of course, what happens? Let's take a look at the 192, and you see here basically that the pinging has stopped and nothing is happening here anymore. Sequence number does not go up. Let's take a look at what we see on our sniffing, and what we basically see here. This is still a live one. You see there are requests and replies going back and forth, but now from this point on, as you see, you only see requests coming in and there are no more replies, and the reason for this is that the traffic is being filtered out. So as you see here, the requests are still generated, but there are no more responses coming. Okay, so our packet filter basically works fine and filters out the ICMP traffic. We now want to stop filtering this traffic and want ICMP to pass through fine again. And the way we do this is by before I do this, let's just take a look at IP tables and check the rule. Here you see the rule. It basically says the target is drop and the protocol is ICMP. We did not care about the interfaces, regardless from where to where. Everything that's ICMP is going to be dropped. So let's now remove this rule. This is a rule which basically F stands for flush, will delete all of the rules which are currently present in the forward chain. And if I start doing this and I take a look what's happening here, then you see all of a sudden here the request replies are going back and forth fine again. So all of this worked well, and we checked that ICMP can basically be filtered out. So far so good. Let me stop the capture here and let us move on to looking at TCP connections. So again, we have a small program that can act as a TCP server, and what I'm going to do now is I'm going to run this program on the 10.2.4.37 server, and I'm also going to run it on 192.168.1.100. So basically I'm going to run the program, Java program that listens on port 80 here, and I'm going to run the program here. So let's start doing this. Okay, so program was started here. Let's also start the program on the client and stop the ping. Okay, let's see whether all of this works out. So the program now runs on both machines. I'm going to check that I can actually connect to both machines by trying this out. And why don't we try this out basically here from the public network, and I could as well just start a packet capture of us accessing the machines. So I'm opening up Firefox, and as you see here, it already contacted this machine, and what I do now is I stop the capture and we take a quick look at what we see here. So we've contacted 10.2.4.37, and what you see here is that what we get back as information from the server is client connected from 172.16.2.20 port 42,718 to 10.2.4.37 port 80, and of course this is exactly what we've expected. Taking a look here at what we see, again we ignore the ARPs, and we also of course have the same redirect because we're contacting the wrong way, going through 172.16.2.4 instead of 5. So what we see here is we see an HTTP SYN, and then we see the SYN ACK, and then we see the ACK. So that is the TCP three-way handshake, and what happens then is you basically see here that there are capital of packages flying by, and that's basically what we can observe here. So again, let's take a look at what happens when we try to contact the other machine. So let's try to contact 192.168.100, where we've also started the server, and well, as you see here, we pretty much get the same information, and of course also the capture shows pretty much the same thing. You see here syn ek, this time not as stupidly disrupted as before because we didn't have the ICMP redirects in here, and then basically there is an information exchange between the client and the server, where in the end the packet is coming out fine. Right, so we can contact from the public server. Let's quickly check that we can actually also contact the machines from one another. So let me contact from 192.168.100 10.2.4.37. Works out fine. And by the same token I can go to the server here and do the same thing. Let's try to contact 192.168.100. Yeah, all of this works out fine. So again, both machines can contact one another, and that's exactly what we've what we basically hoped to achieve. Now, what we now are going to do is we basically want to use a static packet filter configuration as shown before in order to allow outgoing connections from the 10 network into any arbitrary network. So TCP connections outbound should be passing through, and then you should be capable of establishing a connection, whereas inbound TCP connection, in this case a connection from this machine here to the server, are not supposed to work out fine anymore. So what we're going to do is we're basically going to put in the rule for doing this, and the appropriate rule for doing this on our router is basically, or the rule we're going to try out first is basically a rule that would filter out all TCP segments where we have a SYN flag set. So what I'm going to do now is I say IP sudo IP tables forward chain, and what we want to do is if the packet is destined to 10.2.40-24, so for our 10.2.40 network. By the way, this is a rule that you would not typically find in a practical packet filter configuration, because there you would rather not only specify the IP address, but you'd rather specify the interface. So the protocol is TCP, and we are also going to look at the TCP flags, and what we basically want is we want to filter out packets with a set SYN flag, and if we do this we want to drop the packet. We can take a look at this rule in the packet filter. Here you see it. So again, target is drop, protocol TCP from any interface to any interface, regardless from where the packet's coming, no IP address specified. If it is a packet that's destined to 10.2.40.24, then basically if the SYN flag is set, this packet is going to be filtered out. So let's try to see whether this achieves what we actually want to achieve. First thing I'm going to do is I'm going to start a packet capture again on the machine in the public network, and now I'm back to the client in this network here, and what I'm basically going to do is I'm going to click the reload button and see what we get. So I click the reload button, and as you see here it says loading, 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 and as you will soon find out, actually not much good is gonna happen, because basically this connection is going to time out fairly soon. Let's wait until we actually see the timeout here. shouldn't take too long. So yeah, here we have the timeout now, and let's take a look at what we see in the public network. What we sniff, well, basically, as is to be expected, we see the SYN here from 192.168.1.100, but there is no reply because, again, the server doesn't really get it because it's filtered out by the firewall. Server never receives the SYN and does not reply with the SYN ACK. And then, of course, here, as you see, the SYN is sent again and sent again, but again, there's no reply. Well, that was exactly what we wanted to achieve, didn't we? Let's take a look whether outbound connections are working from the 10 network into the 192 network. So let me try to reload this here. And before I do this, let me again stop the packet capture and restart. And now let's try from here. And might come as a surprise for you. You also see loading, and as you will soon see, there also is a timeout occurring. And the question, of course, is why is there a timeout? Well, we're going to check in a couple of seconds why. And well, here it is. So let's take a look at what we've observed in the public network. Here is the packet sniff. So what we see is we see a SYN from 10.2.4.37 to 192.168.1.100. So that goes out fine. Okay. But then what we see here is a reply from 192.168.1.100, which is a SYN ACK, but there is no ACK coming back. And as you see here, there is another SYN and there is another SYN ACK, but somehow the handshake doesn't finish. And the reason for this basically is that this packet here from 192.168.1.100 to 10.2.4.37 is being filtered out by the firewall as well. Why? Because we basically specified that whenever the SYN flag is set, packet is going to be dropped, and the SYN flag is set here as well. There's also the ACK flag set, but we didn't specify that. We just said if the SYN flag is set, then we are going to delete the packet. So that rule was somehow wrong because, again, the second step of the two-way handshake inbound into the 10 network was also filtered out. So we have to revise our rules and change them accordingly on the firewall. So that's what we're gonna do now. Let me first restart the capture here for observing what we have later. And now let's go in here. First thing I do is I flush the rule again, and now we're going to insert another rule where we make one difference here. We don't specify SYN here, we specify SYN ACK and SYN in this case. This rule now tells that in a TCP segment, the SYN and the ACK flag are considered, and the rule matches if and only if the SYN flag is set but the ACK flag is not set. So again, this specifies what's to be observed, SYN and ACK, and the packet is dropped if only the SYN is sent. Whereas in the previous rule we said we only observe SYN, and if this is set, then we're going to drop it, and that obviously was wrong. So we put in this rule, and now let's take a look at what we get. Again, in our reference network, we now specified the filter here, and what we want is we don't want incoming connections and we want to allow outgoing connections. So let's again try first by taking a look at the 192.168.1.100 machine contacting 10.2.4.37. I'm clicking here and you see it says loading, and it's not going to come as a big surprise to you that we're also going to get the same error message here again after a while. Let's take a look at our packet capture on the machine in the public network, where we see the same story again. There is a SYN but no answer. And now of course comes the more interesting part. Does the reverse direction work fine now? So let's take a look. I click on reload, and yes, everything goes through fine. As you see here, all of this now is working. And of course we could also, when we look at the packet capture in the public network, just see that all of this is now working fine. So finally we found the right configuration for what we actually wanted to achieve. Okay, let me restart the packet capture in the public network again. There is one thing else that I briefly want to show you. Up until now we only observed client-side wise that the connection is not going through by observing a timeout. There is another way of doing this. Instead of specifying the drop target, I could also specify reject, and with the reject target there is an error message being sent back from the firewall to the client trying to contact the server. Let's take a look at this now. So if I'm trying to contact from here, you see that immediately I get a response and it says connection failed. Let's take a look at the packet capture here. What you see is you also see the SYN segment being sent, and then you see an ICMP destination unreachable message here, port unreachable, from 172.16.25, which actually is of course the public interface of the router in the 10 network to 192.168.1.100, saying that the destination is not reachable. So that basically is the message that we then are receiving on the client side, and then the client says, oh damn it, something failed. So let's move on from static packet filtering to dynamic packet filtering, and for doing this I'll again go to the router, and what I do is I first flush the forward chain, and what I'm going to do is I'm going to go into the proc directory and then into the net directory, and there we find a file called IP contract, and sudo so here right now we don't find much, but that changes if, for instance, now I'm loading some pages here, and if I now go and take a look, I actually find the TCP connection which just flew through the router here. And basically what can be seen in this IP contract file right here is a TCP connection. First field says it's TCP, and 6 is the protocol number of TCP in the IP header. Linux uses a timeout mechanism to remove no longer existing perished connections from this IP contract file, and you see here this timer is set to 114 right now. As you see here, this is the timing in seconds. The entry is going to remain valid. The length of the timer is chosen depending on the status of the TCP connection. Here we see a TCP connection in the time wait state, which basically means that everything is finished in the TCP connection anyhow. So that's why this is going to be removed fairly fast. If a connection is in the established state, it's gonna linger around for much longer. What else do we see? Well, we see the source port and the destination port for one direction, and the source and destination IP address. We see the number of packets, the number of bytes that were sent, and then we see the same for the reverse direction as well. So again, it is very instructive to look into this file, and as you're gonna see here, 22 seconds from now this connection is going to be removed, 18 seconds from now, 16, let's just see until this connection is removed. Should now immediately be the case. Well, 8 more seconds, so let's wait and see what happens if this is going out of the file, and here you see now the file is empty. Of course there can be numerous connections. If I'm just making a couple of connections from the server side to the client side, and now also in the other direction, and I now check this file here, I should see many more connections all in the time wait state, and as you see here, well, there are quite a few, as is to be expected. So this file keeps track of all the connections, and this is an example of what the IP contract module in Linux allows you to do. Namely, it's tracking communication flows, which is useful for many things, but one thing it's particularly useful for is for filtering out connections with a stateful packet filter. So what we're now going to do is we're now going to use a dynamic or stateful packet filter for filtering out connections. What we want to do is we basically want to achieve the same we had before, namely outgoing connections should pass fine, whereas incoming connections are blocked. And first thing I'm going to do in order to achieve this is I'm going to change the default of the packet filter to drop. How do I do this? Well, I say IP tables minus P, that is the policy of the forward chain, and I change this to drop. See that it worked. Here is accept and the policy still, and here for the forward chain the policy is dropped. That basically means nothing goes out now, nothing comes in. And now I'm adding two rules into the forward chain, which basically are supposed to dynamically allow outgoing connections from the 10240-24 network into arbitrary networks, but not allow incoming connections. How do I do this? Well, sudo IP tables. I'm adding to the forward chain, and what I want is if the source address is 10.2.4 from the 10.2.4.0 network, then I'm using the contract module, and if the connection state, which basically means that new means no packet whatsoever has yet been seen from this connection, then I'm letting this packet pass through. That's good and well. So that basically allows the first packet to pass if it's from the 10.2.4 network, and this here new refers to any packet that does not belong to something that has already been seen before. So in that sense the synac is also already in a packet which belongs to a communication flow which has already been, quote, established, unquote. This is not the TCP state established. And what I'm going to specify now is that in the IP tables, in the forward chain, whenever I see a packet that belongs to something which is established with respect to IP contract, I'm also gonna let it pass through fine. Let's take a look at IP tables. That's how it looks right now. Again, here you see the rule: when something comes in that is new, and if it is from 10.2.4.0-24 network, we let it pass through. If something comes that's related to this, which is basically another packet from the same communication flow, or also the reverse direction counts as this, then it's going to pass fine, and the other direction is, and everything else is not going to be allowed through. Let's check how this works out. So here again is our server on 10.2.4.37, and as you see here, I can contact 192.168.1.100 just fine. What about the reverse direction? Here again we have the client, and as you see here, okay, no connection possible, nothing's working. So that's exactly what we wanted to do, and that shows how dynamic packet filtering, stateful packet filtering, can be used with Linux. It is very instructional to play around with this and try it out. Again, we were only looking into this very shallowly. It makes a lot of sense to also dig into this deeper in lab experiments yourself. So for the next experiment, I will briefly reset the machines here. So first thing I'm going to do is on our router, I'm going to flush the chain again. And what I'm also going to do is I'm going to change the policy again to accept. So now when we take a look, everything should look as before. And if we now check whether this is working here, you see that we can establish connections to 10.24.37 just fine from 192.168.100, and of course in the reverse direction, as you see here, this is also working fine. So for the next experiment, the idea basically is to say, hey, what about having a non-routable address in the 192 network and using a NAT functionality? So the basic idea right now, and again, this is a scenario. In practice, none of these addresses is routable. What we're going to do is we're going to say this 192 network here is a network which is not really known to anybody. Nobody knows where this network here resides. And what we have to do here is this is a private IP address range, and we're going to employ a NAT translating all of these addresses in this network here into this publicly known address for contacting other machines. And we'll see how this works out. In order to implement the NAT, of course, what we need to do is we basically need to also make sure that this machine here, this router, does no longer know how to reach the 192 network. So let me quickly change to the router. Here it is, and if we take a look at the routes, then we basically see here the entry that we can reach 192.168.10 by contacting 172.16.2.4. This entry here basically tells the router how to reach 192.168.10-24. So what we're going to do now is we're going to remove this entry and basically then simulate that the 192.168.10-24 network is a private network. The command to do this is sudo route del -net, and the net is of course 192.168.10-24, and the gateway we used of course was 172.16.2.4. So let's take a look. The route is deleted, and let's just see what the consequences of this are. What I'm going to do basically is we're going to start a packet capture here, and I'm trying to contact now from the 192 network the machine 10.24.37 again, and what you see here is it says loading, but not much is happening. And why is this the case? Well, as you see here, there is no response, because basically the response is not coming because the reverse direction is not working out. We can also sniff here on the server which is supposed to answer. Start a packet capture here as well. So we start a packet capture here, and now let's try to contact again. And if we now take a look on the server, what you see here basically is we don't see anything. No packets are reaching the other machine anymore. Okay, so what we want to do is we want to remedy this situation by now also telling the machine again how to, well, or basically telling the router of the 192.168.100 network to serve as a NAT. So this is the router. We haven't done much on this machine before, but what we now want to do is basically we are going to use NATing here, and basically this is done through IP tables. Let me briefly type in the command IP tables -l -v. So here we see the IP tables, and what we will do now is we will enable netting. So for doing this, what we have to do is we have to say sudo IP tables -t net. -t net refers to the table being the net table. You should also look into this, because basically this is a different type of table which is typically not shown. What we need now is we need -a post routing, and again this adds something to the post routing chain. And what we basically want to do, that's what we have to see in the ifconfig file. What we basically see here is we have two interfaces. One is ETH0 on 192.168.1.5, and we have ETH1 on 172.16.2.4. What we now want to tell the machine is that if the outgoing interface here is this public interface, then we want to use this address for all outgoing machines. So we specify minus the outgoing interface -o ETH1. So if something goes out, then we specify if something goes out on ETH1, we want netting. So we want source netting actually, and of course now we also need to say which address is to be used for the source netting, and this works with --2, and the address we want to use is 172.16.2.4. So now we've enabled netting, and that basically means that what's going to happen now is that IP addresses from this internal network here are supposed to be replaced by this address, which of course then here again is publicly known. So that would mean that from now on this machine could respond fine. So before we try this out, let's start with a packet capture again in order to see what's happening. And now let's see if we use this client here and try to contact 10.2.4.37 what happens. Yeah, and you see that we now get a connection. But if you take a closer look now, it says that we are not connecting from 192.168.1.100 as before. Now what the server sees is that we connect from 172.16.2.4. So basically the netting has been performed. You also see this here, that if we take a look now in the SYN and SYNAC, the handshake and the sending, then this is from 172.16.2.4 to 10.2.4.37. And of course 10.2.4.37 also answers to 172.16.2.4. So now we are using netting functionality in order to achieve the routing, and the 192 network is no longer publicly known. So that's the destination net. I'm sorry, this of course is the source net, and as you probably already expect, if I'm now trying the reverse direction and send something to 192.168.1.100 from here, it says that it's not possible to establish a connection to there, and that's basically just right. Why? Because again, nobody knows how to reach 192.168.1.100. If I'm offering a service on this machine, as I do now on port 80, I basically cannot access this address. I have to refer to this service by the public address here, and then the router here or net here needs to translate the public connection into my private one. So basically there must be a socket here in which I'm waiting for incoming connections, and that then is forwarded to 192.168.1.100. This functionality is also known as destination netting. Let's again go to the router here. Sorry, that's the wrong router. Where do we have it? Here it is. So what I'm going to do now is I'm going to set up destination net, and what I want to do is I say Again, I want to put something into the NAT table. This time I'm going to put it in the pre-routing chain because obviously it happens before the routing decision. Whenever something is TCP and the destination port is 80, that basically means that we are dealing with web traffic which comes in here on port 80, or actually, why don't we say it's coming, which says, why don't we say it comes in on port 8080 here? Makes it a bit more interesting. And when it comes in on the interface ETH0, ETH1, that's of course the interface for which it comes in, then our source is destination NAT, that's the target, --2, we send to 192.168.100 port 80. Okay, that was of course just the missing minus here. Okay, we set it up, and if everything is working, then if we are now contacting 172, so again, what did we do? We set up that everything that comes in here on port 8080 gets netted to 192.168.100 port 80. So if I'm now using 172.16.24 here, and I'm accessing port 8080, I should be forwarded to 192.168.100. Let's see whether that works. Yeah, there we are, and as you see now, I've contacted 172.16.24.80.80, and I ended up at 192.168.100 port 80. So that basically shows source and destination NAT and how it can be achieved with IP tables. So now that we've covered packet filters in detail, let's focus our attention on application level gateways. Application level gateways are another type of component of firewalls. Why do we need application level gateways? Well, as mentioned before, packet filters are powerful tools, but they're typically only employed up until the transport layer, because filtering application level data with a packet filter is fairly problematic. It makes more sense to not look at the individual packets, but to instead get the information and interpret it on the application level and then filter based on this information. And the types of devices that do this are the so-called application level gateways. Application level gateways do come under many names. They are also coined proxies, for instance, for HTTP, or session border controllers for voice over IP. And the reason for this, of course, is that application level gateways in general, they control the traffic on the application layer, since there is multiple applications that do very different things. Also, the way the application level gateways actually work and in detail work are very different, and that's also why they are named differently. However, the idea in principle is always the same, namely that the connection between the station in the intranet, as shown here on the left side, and the server in the internet, as shown here on the right side, or actually it could also be the reverse order, that the server is in the intranet and the client connecting it is in the internet, because that's also another scenario where application level gateways can be used. So the idea always is that this connection does not happen directly, but instead through an intermediate station which filters the traffic on the and controls the traffic on the application layer. So again, we have rules, what's allowed and what's not allowed. And what happens then is, let's stick for now with the scenario that the client here is in the intranet. The client places the request on the application level gateway, where the application level gateway basically analyzes what happens and then forwards the request to the server in the internet. Apart from security functionality, application level gateways can also do other things. So for instance, application level gateways in form of proxies for HTTP could also cache websites in order to not use the wide area networking link here too often in order to get the same page over and over again from particularly popular websites, for instance. That's one possible way, caching, and therefore, well, effectively optimizing bandwidth usage. But also, of course, there are numerous security functionalities which happen in here. So some of them are already mentioned, as you see here, based on the analysis of the request and what's coming in. There could be access control, so the application level gateway could only allow requests to particular domains, and whereas a packet filter typically is blocking on an IP address base, for an application level gateway it's also possible to filter based on domain names, for instance. The content here, in terms of the information which is being sent, can be checked, for instance, to detect malware in web pages, or you could also think of this as an email server, which is also working as a gateway because email is basically fetched from here and sent through here as well. So detecting malware, logging of course is important. An application level gateway can log what's happening here, and that of course also implies that with respect to the internet clients, each and every individual access to a website could be logged. Now, this is of course not as harmless as it sounds. It has a lot of implications with respect to data protection, because if an application level gateway is configured that way, each and every web page user requests could be logged and stored and then later on analyzed, for instance by superiors who want to check how much private surfing an employee did, for instance, in case of HTTP. So what's good about an application level gateway is, again, since it's directly contacted, all of the information is extracted and then presented on the application layer, so we don't have to deal with individual packets. We don't really need to worry about fragmentation or other things. We can basically just get the information here as a whole. So the advantages of an application level gateway over a packet filter are in particular, and again let's note those down right now, as we did before. If you have an application level gateway, then of course it's also possible to filter the data based on user specific rules. So application level gateway allow for user specific rules. How can user specific rules be enforced? Well, you could, for instance, require users to log into the application level gateway before things happen, and then based on the login you could also have different roles and rights which are assigned on the application level gateway. So you have a much more fine-grained control over communication partners and application functions. So let's just sum this up here as fine-grained control. Next thing which needs to be mentioned is application level gateways are very good for checking the content, for instance, in order to detect malware before handling or before handing it over to the user that requested, for instance, a website or email or whatever. So content checking is something that can be done. And Another thing which is important is that by not having a direct connection between sender and receiver, that can also lead to a certain anonymization of the traffic, because all contacts between the institution and external servers will go through the application level gateway. So let's also put this down here, no direct connection between sender and receiver. Last but not least, and again, this is not only good logging. Application level gateways can work in multiple configurations. They can also work transparently, which basically means that the user is not aware of the fact that an application level gateway is doing something, and the machines are not configured that way, but the data is basically just rerouted to the application level gateway. However, in most cases, application level gateways do not work transparently and are explicitly also put into the respective configuration files of the applications which have to send that traffic through the application level gateway. So application level gateways also have certain disadvantages which should be mentioned. One is, of course, that they are very application specific. So what does this mean? Well, it means that an application level gateway for HTTP cannot be used for anything but HTTP, and that also means if you have a couple of applications, then you have a couple of application level gateways. And the next thing is that application level gateway are exposed to attacks, because basically, since they are often very visible from the outside, then application level gateways are much more prone to being attacked as opposed to packet filters, because packet filters basically don't offer much of a footprint for an attack. They simply filter packets, whereas application level gateways have much more functionality and could therefore also be supported and attacked. So in praxis, there are numerous firewalls which basically consist always of packet filters, and then they also have application filter or application level gateway functionality. All of this can reside on different machines. It can reside on a single machine. In practice, there are multiple ways of how this could be done, and you'll basically find a lot of different types of implementations of this in practice. So let's move away from application level gateways and go to firewall architectures and start discussing how firewalls are actually put into practice. And this slide here shows a very simple firewall structure where we basically have the internet, and this here is the boundary between the internet and the intranet. So there is a router, we have some servers which are accessible from the internet, and since they're supposed to be accessible from the internet, we did not put them behind the packet filter right now. And then here we have our packet filter, which is protecting the protected internal network. Behind this packet filter, you might have some servers which are only accessible from the internet. And what we're going to discuss in the following is the question: how do we best position the servers which are supposed to be accessible from the internet, and where would we, for instance, place an application level gateway, which basically is pretty much a server that also needs to be accessible from the internet with respect to many features. Where can we actually place them? Well, we have two choices. One is, we put it before the packet filter, as is shown here, and before, of course, from the view of the internet. Or another idea would be to place it behind the packet filter. Well, so where do we best position it? And of course, when you see this, then it's pretty clear that this positioning is somewhat problematic because the servers are not granted any protection by the packet filters, so they are fully exposed to the internet and to attacks, and it would be nice to have a packet filter that would at least limit communication attempts to the ports which are actually to be used from the outside. So if you have a server, for instance, the server might have an SSH connection to it where you can access a remote shell, but that's only supposed to be used from the intranet, and here there is no way of being able to filter that out. So why don't we just put the servers behind the packet filter into the protected internal network and then open up a port on the packet filter? Well, if we do this, then we bump into another problem, namely that the server accessible from the outside might still be attacked from the internet on the port where it's actually supposed to be contacted, and then this server, once it's compromised, has unlimited access to the, well, protected internal network, and then could subvert all other machines which are positioned in this network. So this is not really a good idea either, so that's why there was a third type of solution, which is the use of a so-called DMZ, demilitarized zone. What is the demilitarized zone? Well, the demilitarized zone is a zone which is protected from the internet by a packet filter and which is also separated from the protected internal network by another packet filter. And the idea here is that this packet filter, of course, can offer fine-grained control, what type of access is possible from these servers or from the internet to these servers, and then this firewall, this packet filter here can have fine-grained control as to what these servers are allowed to access here in the protected internal network, or basically prohibit access altogether. So this basically allows, on one hand, to also protect the servers which are supposed to be accessible from the internet somewhat, and as well protects the internal network. Of course, it also makes a lot of sense to further separate the demilitarized zone and other networks, as shown here. We could have different zones such that if one machine which sits in a demilitarized zone is compromised, no other machines in the demilitarized zone are compromised. So this is a great simplification over what you would basically see in practice. However, I think it's enough for you to know this in order to then also be able to understand further ideas as to why particular firewalls are configured the way they are configured architecture-wise. And that's why we're going to not dig deeper into the subject of how firewalls are best constructed in terms of architecture. So now we've covered components of firewalls, we covered firewall architectures, and we looked into particularly packet filters in detail. It's time to take one step back and look into potential weaknesses in the concept of firewalls. So we already discussed some of them when we discussed limitations of packet filters, and that even if you have a firewall, this should not give rise to dropping any other security mechanism in place. However, here we would now like to address particular issues with respect to circumventing the firewall through portable devices such as laptops, PDAs, and of course increasingly smartphones, and the use of tunneling and encryption. So let's start with mobile devices. So a firewall, of course, controls the traffic between the network of an institution and the internet, and might filter out unwanted traffic and have all sorts of filtering functionality, also filter out malware and so on and so forth. However, mobile devices, by their very nature, do not remain in the premises of the company and would also gain access to the network through use of the internet and also public internet access, such as, for instance, a WLAN that is publicly shared, let's say, in a train or other Wi-Fi hotspot. You might also use a DSL connection to connect to the internet, or the connection in another company or whatever. However, when you do this, you are outside of the protected network of the institution, and that of course also implies that usually these machines then are also not protected by the firewall of the institution. Mobile devices which use foreign networks without the protection of the firewall of the own institution might be subject to attacks. Particularly in public networks, there is a big threat that somebody might have set up this network maliciously in order to infest the machines that connect to the network with malware. And it is very common that the networks which are publicly operated don't really focus much on security. And if the network you gain access to is insufficiently protected against intrusions from the outside, then even some hacker might contact the hotspot network through the internet and then infect devices which are connected to the public network with malware. So you should of course be careful if you do that. However, if somebody carries the mobile device across the firewall and switches it on, operates it in another network, then the mobile device might get infected, and once it's brought back to the company, it's already behind the firewall where it will connect to the intranet, and whatever mechanisms we discussed in terms of firewalling will not be applicable to this device when it's accessing machines within the intranet, because the traffic that runs within the intranet does not go over the firewall. And this basically means that there is a threat for all of the machines which are in the quote secure intranet unquote, because as you see here, it's not really a machine, it's not really a safe haven, because these things typically really do happen. So how could this be remedied? Well, one thing is clear: the device which is being operated within the company's network is a legitimate device that belongs into the company network. And so the threat is not the device, it is the data on the device and the altered programs which are the problem. That's why some IT vendors started to also achieve access control based on the content of a device, and to also check that devices which connect to the local network have the required patches and updates. That is a starting point. However, these approaches are out there for quite a while and they haven't caught on yet because there are lots of technical problems with this. So to sum up, devices which are being carried over the firewall and operated in public networks might get infected by malware being taken back to the company, where they then gain network access and could also threaten the devices which sit behind the firewall. So again, firewall is not a safe haven where no infections can occur. Alright, so another issue I'd like to address here are tunnels and encryption. As with mobile devices, tunnels and encryption per se are not only threats, they are pretty useful in many respects. Well, first of all, what is tunneling to begin with? And let us look into a very simple scenario of what tunneling is. We'll look into tunneling and encapsulation in a lot of detail in the next chapter when we deal with virtual private networks, which is basically a tunneling and encapsulation technique. However, here we're going to look at tunneling more on the transport or application layer respectively. So what is tunneling? Let's look into an example here. And the example I want to consider is the use of different port numbers. So let us simply look here into this picture. So let's just assume that somebody wants to access TCP port 110 on a server, that is the POP port here in the internet. However, the firewall is being configured such that TCP port 110 is blocked. Well, fairly simple. If this server, instead of using port 110, would use port 80 for incoming connections, and this packet filter here is basically just blocking port 110 but not port 80, then port 80 could be used instead of port 110. That means by using a different port number, firewall mechanisms can be circumvented, because again, that different applications use different transport protocol ports is just a convention. There is no technical necessity for doing it exactly that way. If the server and the client agree to use other ports, that is all good and well. That, however, is not yet tunneling. Let's look into a more intricate scenario of tunneling, and the example I'm also choosing is tunnel some other protocol. In the example depicted here, also POP via HTTP, Hypertext Transfer Protocol, or I should actually say in this case here something that looks like Hypertext Transfer Protocol. So what we want to do here is we basically want to tunnel the POP traffic, which again, remember, POP is a protocol for fetching email from a server, through the use of HTTP. And how this basically happens through tunneling is as follows. Here we have an email client user agent on the machine. What this machine basically does is no reconfiguration of the user agent needed. The user agent here wants to contact the machine Y, but it cannot contact Y directly because the firewall only allows HTTP traffic, and not only through packet filtering will it ensure that only its traffic on TCP port 80, but the firewall here is configured to also consist of an application level gateway, in this case HTTP proxy, which will happily forward HTTP requests to the internet on behalf of the client. Let's also assume that there is just a basic syntax check running on this proxy. So what happens now is, again, A wants to fetch email here from the server Y, and in the following example we will not change A, we will not change Y. Those will basically run untouched without further changes, except for one thing. We do need to change the configuration to A, and basically change the configuration to A such that instead of contacting Y directly, when email needs to be fetched, A will actually contact B on the right port for POP, which in this case is 110. So as viewed from the email program running here on A, B is the email server. However, that's not quite the case. What B really does is B is a tunnel server and provides a tunneling service that will take POP requests here on port 110, then encapsulate and tunnel the POP traffic into HTTP. And again, syntactically, tunneling something through HTTP can very often be done very easily and has been done for most protocols which are around. So B then tunnels these POP requests by embedding them into a properly looking HTTP request, and then sends that out to a server X, which resides in the internet. Now, B of course does not contact X directly. Remember, direct HTTP connections are not allowed. So B will send the traffic to the application level gateway, HTTP proxy here, and that proxy will inspect the HTTP request which was sent here, but that looks fine. It's real HTTP syntax, does not contain anything malicious, so it's being forwarded to this machine X. X is also a tunnel server, which basically does the opposite of what B does, namely it decapsulates the tunnel POP request out of the HTTP request and then will forward this request on behalf of, well, in this case A, and send it to Y. So, well, that's basically how A contacts Y, although no direct connection here in the internet is possible through the proxy. How does the reverse connection happen? Well, basically exactly the same thing. Data flows from Y to X. From X, B basically keeps a HTTP connection open, goes into polling mode, receives the data here, and then sends it back to A. So what could, from the view of the system administrator that might not like this, be done against this? Well, take a look at the picture. Obviously, what the administrator controls is the packet filter and the proxy. So what could be done? Well, of course, the administrator could step the proxy one notch up and basically inspect and check that it finds out the fake requests which actually embed POP. But of course, then the syntax could be changed by the servers. And if I filtered out based on domain names or IP addresses, that would be the same. So basically, it is a run that nobody can really win, and the administrator will have a really hard time trying to basically allow stuff out of the firewall while at the same time not allowing anybody to tunnel traffic. But that isn't even the worst part. The worst part is that, of course, the information which is being sent through the tunnel could also be encrypted. And if the traffic is encrypted, then at least if the encryption is end-to-end and nobody's breaking the encryption in between, then the proxy has no chance of finding out what's actually in the tunnel and can basically not do anything against this. Firewalls operating somewhere in the network cannot draw any conclusions from encrypted traffic as to what the content of the encrypted traffic is. They might see the communication peers, but as long as the firewall does not break end-to-end encryption and basically does what is pretty much equivalent to a man-in-the-middle attack, the firewall cannot see anything what is happening in the proxy. And that also means that the firewall has basically no filtering capabilities. So encrypted information going back and through the firewall can be considered highly problematic. However, we've discussed already numerous times that, of course, encryption in general is good and that users should encrypt their traffic and that they should do it end-to-end. So in a sense, there is a trade-off between the firewall being able to inspect stuff and the stuff being sent unencrypted over the internet. And of course, there are approaches of basically having the firewall sit in the middle and have the firewall, well, basically act as man in the middle and have an encrypted connection to the intranet and then an encrypted connection to the internet and then analyzing content still. But in general, it's fair to say that this is not a very good idea because it breaks end-to-end encryption, and breaking end-to-end encryption is something that just should not be done. Okay, so one final word regarding personal firewalls. So quickly note this down here. Last topic, personal firewalls. So far, we've considered firewalls which sit somewhere in the network. However, sometimes it is a good idea to not have a firewall that sits on a network, but rather have a firewall that sits on an endpoint, such as a PC or laptop. That is particularly useful if this machine is operated in an unsecure environment, such as a public network. And programs that have this firewalling functionality on an endpoint are called personal firewalls. Personal firewall basically sits on the boundary between the machine and the network, and then again does what a firewall does, namely it controls the traffic between the machine and the network according to certain rules or policies, just like a firewall. If the server is offering a service, basically works as server, then of course this service can only be contacted from the network if the personal firewall is configured accordingly. The working principle of personal firewall is very similar to packet filters. However, of course, they do have access to specific information from the endpoint. So for instance, it could be taken into account which process was actually generating traffic. And that could, for instance, be used to say that HTTP traffic on the TCP port 80 HTTP port is only allowed from, let's say, Firefox, but is not allowed from other programs that might want to use this port for allowing an update. Personal firewalls are typically administered by the user himself, which is very, very problematic since the user typically lacks the type of knowledge and know-how which is necessary to operate such a firewall. Many firewalls bug the user whenever there is a connection attempt and would like the user to say yes or no. And of course, they don't do this once, they don't do this twice, they do this numerous times. And for a user, it is very hard to assess each time thoroughly whether this connection is really wanted or unwanted. And making a wrong decision will have catastrophic or fatal consequences once in a while. Furthermore, since a personal firewall runs on an endpoint and the endpoint might be affected by malware, if this is the case, then the personal firewall might also not run properly because it's also affected through the malware. So if a machine is compromised, firewall could also be compromised. If the machine offers some type of service functionality, then it is a question why it would make sense to really use a firewall to filter out incoming connections, because basically if you don't want the incoming connections, it's better to switch off the service as opposed to restrict access to it by raising the firewall and not allowing connections through. So basically, for outgoing connectors, users are bugged with lots of questions they cannot answer properly, and for incoming connections it would much more sense to switch off services. So in that sense, one can argue that personal firewalls are not that useful after all. However, if you are operating a machine in a public network and you're not sure whether this network is a safe network for you to operate in, then it does make sense to have a personal firewall on the machine. So let's briefly summarize. Again, firewalls control and protocol communication between the internet and the intranet of an institution according to certain policies. According to these policies or rule, there is a distinction between wanted and unwanted traffic, and unwanted traffic is typically filtered out through the firewall, either by means of a packet filter, which is one component of the firewall operating on the network layer, or through application level gateways, which is another type of component of a firewall, which is operating on the application layer. While application layer gateways can filter much more fine-grained and granularly than packet filters and allow for a much better filtering, they are harder to operate, basically because they are application specific and must be tailored to the exact application in question. With respect to the architecture of firewalls, we looked into fundamental reasons as to why we need a demilitarized zone, which is basically a zone protected by a packet filter from the internet and protected by a packet filter against the intranet itself. Firewalls do have intrinsical problems which also allow to circumvent firewalls or can make the use of firewalls doubtful. However, firewalls as a layer of security do make sense. However, just because one operates a firewall does not mean that any other security mechanism which would need to be in place without the firewall could be switched off. You still need those in addition. So, that was today's lecture on firewall. Thank you for your attention and see you next time.